Okay, so here they're saying that the mole fraction of the solute in 12 molar solution of sodium carbonate in water as solvent is going to be what? Okay, they've given you just one condensed statement, but there's so much information in that statement. So they're saying that you have a 12 molar solution of sodium carbonate in water. First of all, let's just take a moment to understand that that is super concentrated. Okay, so yeah, you have that. You need to calculate the mole fraction of solute, right? So what is your solute? Sodium carbonate. You need to calculate the mole fraction of sodium carbonate. What is sodium carbonate commonly known as? Washing soda, okay? Okay, so you have to find out this value, which is nothing but number of moles of Na2CO3 divided by total number of moles, that is number of moles of Na2CO3 plus number of moles of water, because it's a solution of a sodium carbonate in water. Okay, and see, they're telling you that the given solution is of a 12 molar concentration. Okay, what does it mean? You have 12 moles of sodium carbonate in 1 kg of solvent. Your solvent is water. Okay, now you have 1 kg of water given to you, right? So in 1 kg, how many moles of water do you have? You can find that out, and directly we can get started onto this. Okay, so let's first calculate the number of moles of water. The given mass is 1000 grams divided by molar mass is going to be 18 gram per mole. Okay, so now when you calculate this, I don't want to solve the entire thing. I want to keep it as short as possible. So you can see that 18 into 5 is 90. So 18 into 50 is going to be 900, right? If I add 90, I get 990. So from 1000, if I subtract 990, basically I have just 10 left, right? Which again, I can write it as 0.5, okay, and get away with it. So basically, my number of moles is going to come out to be 55.5. Okay, so I have 55.5 moles of water. So I have number of moles of sodium carbonate, I have number of moles of water. What am I waiting for? I can find out the number of moles. I can find out the mole fraction of sodium carbonate, right? So let's see. Na2CO3. This is going to be 12 as given in the question divided by 12 plus 55.5. Okay, so you have 12 divided by 67.5, correct? So see, this 67.5, I want to cancel it out. How can I cancel it out? See, I know that 12 by 60 is 1 by 5, right? 1 by 5 is 0.2. However, my denominator has 67.5 instead of 60. So I'm going to try and approximate. I'm going to very roughly say that the value that I get will be less than, this has to be around 0.2, but I want a slightly lesser value, right? Something around 0.18, 0.19, preferably something between 0.18 and 0.19. Okay, that's just the level of accuracy I'm willing to go to. I don't want to be completely precise about my answer, okay, because I have to save time, right? Okay, so I want a value as close as possible to 0.2, and you have option A, 0.822. This is wrong. Okay, if you mark this, you're basically going for the mole fraction of water, not for the mole fraction of sodium carbonate. Okay, so option A can be eliminated. Option B is saying 0.177. 0.177 in normal circumstances, if you have to approximate it, you can comfortably approximate it to 0.2. Okay, so this is sort of what I'm going for. Option B, 1.77. Do you understand that this is this practically does not make any sense, right? Why? Because they're saying that mole fraction is greater than 1. You know that mole fraction cannot exceed 1, right? Because sum of mole fraction of all components has to be equal to 1. Okay, so this, no, doesn't make sense, right? Then you have option D, 0.0177. This is 1/10 of the value that we were expecting. So you can ignore this. So option B, 0.177 is going to be the right answer to this question. Okay, so here they're saying the value of N of the highest excited state that an electron of hydrogen atom in the ground state can reach when 12.09 electron volt energy is given to the hydrogen atom is going to be what? Okay, so what is important? You need to take note of the fact that they're saying hydrogen atom, they're saying ground state of the hydrogen atom. So basically, your species currently is H, okay, which means your Z is equal to 1. You have to find out what your N excited or your N final is going to be, right? They have told you that they are giving 12.09 electron volts of energy, okay? Why does this matter to us? Basically, if I say that your electron is in the ground state of the hydrogen atom. So which means my initial conditions are such that you have Z is equal to 1 and you have N is equal to 1. Okay. Now, when you have Z is equal to 1, N is equal to 1, basically your E becomes equal to E naught. So your energy is minus 13.6 electron volts. So energy of the electron revolving in N is equal to 1 of the hydrogen atom is going to be minus 13.6 electron volts. So now I am supplying 12.09 electron volts of energy to the atom, or I can say I'm supplying it to the electron. Okay. So when I'm supplying it to the electron, what is the best case scenario of the usage of that energy? The best case is that all the energy will get absorbed and the electron will get to some higher energy state or higher excited state. Okay, this is the best usage of the entire energy according to the question. Okay, right? So you have to find out E final. Your E final is going to be what? E initial plus 12.09 electron volts of energy. Okay, so final energy is going to be initial energy of the electron plus the energy that we have supplied. So let's see what that is coming out. So minus 13.6 plus 12.09 electron volts. Okay, that's basically like saying 13.6 minus 12.09, which when you calculate, you get minus 1.51 electron volts. Okay, so this is your final energy. You have Z is equal to 1, so Z is not going to change anyway. You have to calculate N final from here. How will you do that? Basically, you know that N square is going to be E initial by E final, right? Or E naught. Here E initial and E naught is the same value, so it doesn't matter. But E naught by E final is going to be your N square. Okay. So what is your E naught? Minus 13.6 electron volts. Okay. What is your E final? E final is minus 1.51 electron volts, right? So basically, you're getting a dimensionless quantity, which is okay because N should not have any dimensions. Now, I know it's been a long time since we solved problems of atomic structure, but I hope you remember this. This cancels out perfectly and gives you 9. Okay, so your N square comes out to be equal to 9. However, don't take my word for it. You can pause the video for a minute and you can try and calculate. I am sure that you will arrive at this value. Okay, so you get N square is equal to 9. Right? Now, what does it mean? Means that N is going to be equal to plus or minus 3. So, in our understanding of atomic structure, minus 3 has no meaning, right? So, N is going to be plus 3, right? Which means, what is the highest excited state the electron can take? N is equal to 3, right? Why? Because the highest excited state that the electron can reach is when all the energy will be absorbed by the electron. Okay, so all the energy can be absorbed by the electron and it can go to N is equal to 3, which is the highest excited state. So second excited state or third energy level, which means option C, 3 is going to be the right answer to this question. Okay, so here they're saying that diagonal relationship is shown by, right? Before I even move on to the options, first let's actually recall where we have studied about diagonal relationship. Just give me a minute. Okay, so where have we studied diagonal relationship? Recall the chapter periodic properties. What is diagonal relationship? Basically, due to similar properties, right? Due to similar radius and charge properties, what happens is certain elements which do not belong to the same group start showing similar properties. Okay, so when I say it like that, it sounds very arbitrary. So I will actually write my S and P block elements and show it to you, because S and P block elements is where we majorly find diagonal relationships. Okay, so let me start with group 1A. What do I have in group 1A? I have lithium, sodium, potassium, rubidium, cesium. Okay, I'm ignoring the radioactive ones. Then comes my group 2A. I have beryllium, magnesium, I have calcium, I have strontium and barium. Okay, then what else do I have? I have lithium, beryllium, carbon, nitrogen, oxygen, fluorine, right? And what do I have after carbon? I have silicon. Oh, once again, we forgot group 13. My bad. I'm so sorry. We have boron here. We have aluminium. We have gallium, indium, and thallium. Then we have carbon, nitrogen, oxygen, fluorine. Then we have silicon, phosphorus, sulfur, chlorine, right? Oxygen, sulfur, selenium, tellurium. Then you have nitrogen, phosphorus, arsenic, antimony. You have fluorine, chlorine, bromine, and iodine. Okay, so I have carbon, silicon, then I have germanium, then I have tin and lead. Okay, so yeah, that's all I care about basically. Even these, if you don't talk about, it's fine, right? So these are your elements which majorly concern diagonal relationship. So due to diagonal relationship, I know that lithium and magnesium have similar properties. I know that beryllium and aluminium have similar properties. I know that boron and silicon have similar properties. Okay, these things I know. But can I say that due to diagonal relationship, germanium and antimony have similar properties? Or can I say that selenium and iodine have similar properties? Can I apply it everywhere? No. So what is important about diagonal relationship? Very, very important. It is shown only by second and third period elements. Okay, this is one very important thing about diagonal relationship, that only second and third period elements show this relationship, right? Your first period is hydrogen, helium. This is your second period. This is your third period, right? And these are the only two places where you see diagonal relationship. Don't try to apply it here like I did for germanium and antimony, selenium and iodine. No, that's not how it works. Rest everything, like here, this is the group properties that are followed, right? Similarly, here, this follows group 2A properties. Lithium sort of behaves like a group 2A element, okay? But your magnesium, calcium, strontium, barium, they follow their own properties. They are fine, right? Understood? So that's what happens. This does not happen, okay? This does not happen. Diagonal relationship is observed only in second and third period elements, right? So now let's look for that in the options, okay? So let's see, all elements with their diagonally opposite elements. No, this is the very first thing to keep in mind, that this is incorrect. You can't apply it everywhere. All elements of the third and fourth periods. Third and fourth periods, basically they're saying that maybe sodium and calcium. Do you have this as a diagonal relationship? No, you don't. So this is incorrect. Option C, some elements of second and third periods. Okay, so some elements, this is very important, that some elements only show this relationship, right? So option C is correct. Then you have option D, elements of D block. So you see, we are only speaking about S and P block. D block is not even being considered, because in D block, when you talk about it, there's a lot of other complex stuff, but majorly your D electrons are the ones that are contributing to their major property, which is metallic nature. Okay, so this is not correct. Okay, so the right answer to this question is going to be option C. Okay, so here in this question, they're saying that a 10-gram sample of a mixture of calcium chloride and sodium chloride is treated with sodium carbonate to precipitate the calcium as calcium carbonate. Fine. This calcium carbonate is heated to convert all of the calcium to calcium oxide, and the final mass of calcium oxide is 1.62 grams. Okay. The percentage by mass of calcium chloride in the original mixture is going to be what? Okay. So basically, they are talking about an impure mixture. Okay, so I can say that calcium chloride is what I want, and sodium chloride, I can treat it as an impurity. Okay, so I am treating calcium chloride with sodium carbonate. Because this is my desired reaction, I am treating sodium chloride as an impurity. Okay, so you get calcium carbonate plus sodium chloride, and this is precipitated. So you have calcium carbonate and you heat it. Okay, you heat it, it dissociates, right? It decomposes, you get calcium oxide plus carbon dioxide. They have given you the final mass of calcium oxide. They are saying that it is 1.62 grams. Okay, so this is 1.62 grams. This is all we know. They want you to find out the percentage of calcium chloride in the original mixture. Okay, so what we'll do here is we'll use a simple moles ratio, but let's see. Okay, they have not mentioned anything about percentage yield of the reaction, okay, which is what I was looking for, because then we would also have to factor that in. So since they have not mentioned anything about the percentage yield of the reaction, I can safely assume that my reaction is operating at 100% yield, okay. So now see, I can say that 1 mole of calcium oxide is coming from 1 mole of calcium carbonate, because second reaction is balanced, okay. For the first reaction, okay, it's now balanced. So I can say that the same 1 mole of calcium carbonate was here, and that 1 mole of calcium carbonate is coming from 1 mole of calcium chloride, okay. So basically at 100% yield, I can say that 1 mole of calcium chloride will give me 1 mole of calcium oxide after following the entire scheme of reaction, correct? So basically, now I'll convert this to weight, okay. What is the molar mass of calcium chloride? See, it'll be 40 plus 2 into 35.5, that's 71. So 40 plus 71, nothing but 111. So I'm saying that 111 grams of calcium chloride should give me calcium oxide. So 40 plus 16, 56 grams of calcium oxide, right? Some x grams of calcium chloride gave me 1.62 grams of calcium oxide. I need to find out x. Okay, simple unitary method. So we'll do cross multiplication. So I'll do 1.62 multiplied by 111 divided by 56. Correct? How much is this coming out to be? See, 56 into 2 is 112. You have 111. I can safely say that this is almost, okay. I have 1.62 into 2. Okay, 1.62 into 2 is going to give you what? 4, 2, 3. 3.24 grams of calcium chloride is what they started off with. Okay, so I had 3.24 grams of calcium chloride in the original mixture. Mass of the original mixture is given to you as 10 grams. So this divided by 10. Percentage, so into 100. What do you get? 32.4%. Okay, is there a close value? Yes, we have option B 32.1%. We got 32.4%, but I hope you understand that that is because I took 111 to be approximately 112, which is why you got this very small discrepancy, but otherwise this is okay. So option B 32.1% is going to be the right answer to this question. Alright, so here they're saying calculate the oxidation number of the underlined elements in the following compounds, okay, and your compound is given to you as K4P2O7. And what is the underlined element? You have phosphorus as the underlined element, okay. So let's assume that phosphorus has an oxidation state of X here, right? We'll assume that phosphorus has an oxidation state of X, okay. Now you have to find out, basically you have to find out X, right? So you know that potassium in any compound is going to show an oxidation state of +1. Okay, because this is the general tendency of your first group elements. What are your first group elements? If you look back at the periodic table, your first group elements will be lithium, sodium, potassium, what else? Rubidium, and then you have cesium and then francium, right? Francium we generally don't consider because it's radioactive. So potassium is right here, atomic number 19, right? And it's a general first A group tendency to show the oxidation state of +1 in their compounds, okay. Then you have oxygen, which we'll assume has an oxidation state of -2, right? So now let's get started. You have 4, that is number of potassium atoms, multiplied by +1 charge on each potassium atom, plus 2 number of phosphorus atoms into X is the charge on each phosphorus atom, plus 7 number of oxygen atoms multiplied by -2. This is the charge on each oxygen atom. So we have to solve for X. So you have 4 plus 2x minus 14 is equal to 0. So you have 4. Okay, so you have 2x minus 10 is equal to 0. So you have x is equal to +5. Okay, and +5 is being suggested here in option A. So option A +5 is going to be the right answer to this question.